Welcome back to COSC 2325. This is Chapter 8, our last chapter for the semester. We're going to be covering advanced procedures. So in this chapter, we're going to look at how high-level languages store the parameters and the arguments that are passed to functions. We're going to look and see how the local variables are stored on the stack. We'll review how when we return foreign function, how that happens, how the CPU knows where to return to once we call a function. And then we're going to look at recursion. We're going to create procedures using a prototype, which if you took C++ or C programming, you've created prototypes before. So we'll create prototypes and we'll create procedures that we can pass variables or to the procedure, not just through the stack. And then we'll look at creating some programs that has multiple procedures. And lastly, through your discussion, you'll be learning about Java bytecodes. Okay, so we're going to start with the stack frame. So we've talked about the stack, and we looked at the stack in Chapter 5. And we looked at how whenever you call a procedure, the minute that call is made, the address to where that procedure returns to is pushed onto the stack. And then we also saw how we can push different registers onto the stack that maybe we'll use in the procedure itself so that we can save the values, reuse the registers, and then restore the values at the end of a procedure. So whenever you have multiple procedures in a program, there are multiple stack frames that are on that stack. So stack frame, also known as an activation record, is just a certain amount of space that is set aside for each procedure, and each procedure has enough space to put the parameters that we're passing to the function, the return address, any registers that are being used, and any local variables in a function. So the stack frame is just part of the stack, and it's just a certain section of the stack. So each procedure gets its own little section. So whenever we have a stack frame, there's different steps that we follow. So first, the calling program pushes arguments on the stack and calls the procedure. So like if I call a function sum and I pass it 5, 6, the 5 and the 6 are pushed onto the stack. Then once those arguments are pushed onto the stack, which is not listed on here, but the return address, so where to return to, is pushed onto the stack. After that, then the base pointer. So this base pointer here is this base pointer for this stack frame. And what that is just basically saying, here's the end of the stack frame. And it just allows us to know where the procedure ends on the stack frame. And then we know that there's a stack pointer at the same time, and the stack pointer just moves down as we push different things on the stack. So the stack pointer is is assigned or moved to EBP. So EBP and ESP will point to the same spot. And then if we have any local variables, EBP is going to move. And I'll show you how that works. So the stack frame is created by the following sequential steps. Pass arguments. So this is actually all the different steps. So the arguments are pushed onto the stack. The subroutine is called, causing the subroutine's return address to be pushed on the stack. As the subroutine begins to execute, EBP is pushed onto the stack, which is, it tells us like this is the end of the stack frame for this particular procedure. And then EBP is set equal to ESP. And from this point on, EBP is going to act as a base reference for all of the subroutine parameters. If there are any local variables, ESP is decremented to reserve space. And if any registers need to be saved, they're pushed onto the stack. So let me show you an example of these different steps here, okay? Because we're talking about ESP and EBP and all kinds of stuff. So let's say that we have this C++ program. So here in main, we're calling the add function, and it has two parameters. It has parameter 5 and parameter 6. So the way that C++ works is that whenever you call a function, the parameters are pushed onto the stack from right to left. So the 6 gets pushed onto the stack first. Let me stop sharing. What did I do? Just a second. Okay. So the 6 gets pushed onto the stack first. So we have a 6 here. And the 5 gets pushed onto the stack. And then the address to the next instruction, this is the next instruction, that address gets pushed on the stack. So I'm going to put return address. And remember that this return address is an EIP. So what gets pushed onto the stack is EIP, because EIP is waiting to know like where to return to. Then EIP gets changed to here. So then we're going to call the function. So we're going to move here. That's the instruction pointer. And also when we're pushing things onto the stack, ESP is the stack pointer. So ESP's here, then ESP moves down once the 5 gets pushed in, and then ESP is moved down. And what ESP holds is ESP holds an address. So remember that each one of these, you think of them like an array. So each one of these is 4 bytes. So let's say that this is 0, 0. This would be 0, 4, the address that it ends ends with this, sorry, we have to go backwards. Let me erase that, that's wrong. So the stack is actually going downwards. So let's say that we start at 0, 8. And then we're going to subtract 4. And then we're going to subtract 4, like that. Okay, so ESP keeps moving down. And then, so then num1, num2 are going to get these values, the 6 and the 5. And then inside here, inside this function, it's just adding num1 plus num2. And oh, the other thing that happens is as soon as you enter the function, is the EBP is placed on the stack. So EBP is, if you look at the address of EBP, it's usually about 18 bytes from ESP. So like if ESP is here, then EBP has an address of like 18 bytes higher than ESP. But basically it's just, we just have this EBP so that we know that this is the end of the stack frame. So this function called add ends here. And once you push EBP onto the stack, of course, ESP moves here. And then we set EBP equal to ESP. So EBP, like the register itself, will do a move and we'll move ESP to EBP. So then you have EBP here. It's saved here, but you have it here with the same address as ESP is pointing. So you've got two things that are pointing to the stack, ESP and this EBP. The original EBP is saved. Now, the reason that that happens is that if you have local variables like we do here, so here we have num1 and num2, these are local variables to add. So these local variables have to be pushed onto the stack. And what will happen is that we will subtract from EBP 4 bytes and we'll add it adds num2 first. So add num2. So it'll subtract 4. So we're here. So, and it'll subtract and it'll add. It's going to make space at the bottom to add the local variables onto the stack. So for right now, we've got 6.5 return address and EBP. Let's not talk about the local variables yet. So whenever we're done with a function, the first thing that we have to do is we have to restore EBP, just in case we pushed EBP down, we restore it. Once we restore EBP, we pop it off by restoring it. So we'll do a pop. Once you pop EBP, then it can return back to this spot right here. So this return address gets popped off automatically when we're done with the function. Depending on the programming language that you're working on, this 6 and the 5 may or may not get cleared on their own. So like in assembly language, we have to clear the 6 and the 5 from the stack. And the way that you clear that is just by bringing ESP to here. So you subtract from ESP, you add to ESP, you add 8 to ESP to bring it up, and that clears the stack. So we'll look at those steps. So whenever you're done with a function, you have to restore EBP, return. So pop this, and then move ESP up. Clear all this. So here's an example of an assembly program. Similar to what we had in C++. So in here, in the main procedure, we push the 6 to the stack and we push the 5 to the stack. So here's 6, and we know ESP's here, stack pointer. And once we push, oh, goodness. Once we push that 6 onto the stack, then the pointer moves down. ESP moves down. And then, so we did that. And then we push the 5. And then ESP moves down. Then we call sum. That call, sum, will push the return address. Return address. Then we go to the sum procedure. So we go here. And we push EBP to the stack. So we say base pointer. Then it moves, oh, and ESP has already moved here. And then ESP is actually here. Actually, ESP is here, sorry. Hasn't moved down yet. So ESP is pointing to there. Then this next step is move ESP to EBP. EBP is a register and it's going to contain whatever the address that ESP points to. So if ESP is pointing to, let's say, 000FA, then EBP will hold 00FA. Place this and make it nice. So we've got ESP is pointing to this spot, and EBP is also pointing to this spot. And that was that step. Then we move, it says go to the second parameter. So here we're saying EBP plus 8. So EBP, here's EBP right here. It's pointing to this spot. So this is EBP plus 4, EBP plus 8. That takes us to the 5. So EBP plus 8 gives us a 5. That 5 gets moved to EAX. So we have EAX, and EAX gets the 5. And then EBP plus 12 gets us to the 6. So here's what, it's not looking at this EBP, it's looking at this one, what it's pointing to. So whatever EBP is pointing to, it's pointing to here. We're going to go up 4, up 8, up 12, and it's going to get us the 6. And that 6 is assigned to EBX. And that's what that is exactly what happens with like this example, the previous example, the C++ example. So let me see if I can get back there. So to get this 6 from the stack to assign it to num1, that's exactly what happened. It was like EBP plus 8 would get the 6 and assign it to num1. EBP plus 12 assigns it to assigns the 5 to num2. Okay, so now EAX has that, EBX has the 6. Then they add EAX and EBX. So then 6 plus 5 is 11. So EAX changes to 11. Okay, then they're done. So once you're done, you've got to restore EBP. So and right now EBP hasn't moved. But it will, and I'll have an example to show you how it moves. But right now it didn't move, but we're going to restore it just in case it has. And so they pop EBP. So the address of the original EBP gets popped off. Oh, actually, it did change. Sorry. It changed to ESP. It did. So the original address of EBP is going to get restored. So I'll just put EBP here. So that's done. Then the return, what the return does is it does a pop. And the return, this has been popped off. So that's EBP has moved up. Excuse me, ESP has moved to here. And because ESP moved to this spot, when we do a pop, it pops off the return address. So pop off the return address, and it returns us to this spot here to the invoke, and we invoke this process. Now, the thing that's missing from here is that the 6 and the 5 stayed on the stack, and the stack did not get cleaned. So to clean off the stack, we would have to add right before the return, we have to move ESP up. So that means that you've got to go ESP plus, so ESP plus 4. So ESP's here. So we're going to do plus 4 plus 8 to put it above here. So after the return address gets popped off, then ESP is pointing here. And then from here, we're going to go ESP plus 4 takes us here. And then plus 4 is going to take us here. So that's a plus 8. So here we're going to do a move, and we're going to move to ESP plus 8. And this right here, this line right here cleans up the stack. Clean the stack right here. So all that has to happen. Now there are assembly, just like in high-level languages, we have some special instructions that will do this for us, where we don't have to do the moves and the pop EBP and the push EBP, and we'll look at what those are. But this is what happens in high-level languages. These pops and these pushes, the EBP, and keeping the stack frame, and for each procedure. So let's take a look at the next slide. Stack parameters. So let's talk about stack parameters. So there's 2 ways that we can have stack parameters. We can have register parameters, so like EAX, EBX, ECX, and we can have variables, right? So memory locations. And I think one thing we had mentioned is that if you have register parameters, that could possibly be faster than memory, because the registers are right on the CPU. And memory, you got to go out to RAM, and you have to retrieve the value from memory. But the problem is that you only have so many registers. And because you only have so many registers, you always have to push the registers onto the stack to then use them in a procedure to then restore them. So you have to save them just in case you mess with them and you need those values when you return. So there's a lot of moving. There's a lot of pushing and popping when we're dealing with registers. So here what they've done is they've kind of showed you two different ways that we could do this. The way that there's a call to this function called dump memory. Dump memory is a function in the Irvine library, and the way that it works is that you have to set these three registers. This is the way that it's coded, okay? This is the way that Kip Irvine coded this procedure. So in ESI, you keep the offset of the array. So you keep where the array begins. And basically what you're doing, dump memory just dumps the memory of anything you want to dump, okay? So like an array. So let's say that the array has 10 elements, then the length of array here, you would put it in ECX would be 10. And the type, well, that depends on how you define your array. Is it a byte array, a double word, a word? So ESI, ECX, and EBX are used by dump mem. And to be able to call dump mem, you always want to push AD. Basically, you're pushing all the registers onto the stack, saving them, changing them, calling dump memory, restoring the registers. Just in case prior to this code, maybe you had ESI set to something special. Maybe you had ECX set to something special. This is overriding them. So it says, what if we changed dump memory and we didn't use it this way? Now, we don't use dump memory this way. It's not written this way, but let's say that we did. And let's say that instead of moving stuff to a register, you would just push the three values onto the stack like they were being passed as parameters, like I just did add 5, 6. Here would be called dump mem, and you would pass it 3 numbers. So you'd pass it the offset of the array, the length, and the type. So you only have 3 pushes. You call dump mem. Here you have to push all the registers, or maybe you could just push these 3, but you'd have to push all 3, do the moves, and then pop them to restore them. So it is more moving around. Using registers clutters up your code. It has a lot, you're gonna have a lot more code because you have to do a lot of pushing and popping to save and restore your registers. So there's some give and take in C++. You have a combination. So C++ uses a combination of registers and local variables both to make things efficient. Okay, so in this slide, we're just going to look at the difference between passing arguments by value versus passing arguments by reference. So this is having to go back and remember how passing by value versus passing by reference, what's the difference? So if I had a function and my function call is add, and I was passing it the value, well, here they have a function called even or odd. Okay, so that's our function, even or odd. I'll call it EO. And this function, we're passing it val. So if you pass val by value, you're just passing the value of val. So val has a value of 5, and it gets passed to num. And so num gets created in memory. So you have val is in memory, num is in memory. They each hold a number 5. But if you were to change num in this function, it doesn't affect val because val has its own address. When you pass by reference, when you define the function, if you remember, like when you define the function even or odd, you put the and sign like this, int val. And what that means is that you're not passing the 5, you're passing the address of val. So what you're passing is this FFE0. and that FFE0 gets stored in num. So num is a pointer to val. See, num points to val because it holds the address. So anything that you do to num, any changes you make to num are going to affect val because num holds the address of val. So that's passing by reference. So when you do this on the stack, that's the same thing that's happening. So what you're moving to the stack is not a 5 or 6. What you're moving to the stack is going to be an address. And the next two slides give you an example of that. So here's an example of passing by value. Again, when you're pushing by value, you're just pushing 6 and 5. You're pushing the values of them. But when you're passing by reference, you push the offset of the value. Remember, offset gives you the address of this variable in memory. So val2 will contains the address. Offset val2 will get the address of this variable and put it onto the stack. So this is the address of where the 5, the 6 is. This is the address of where the 5 is. So again, this is just a little picture of after we make a call, here's what the stack looks like. So you would either, if your function call has 2 arguments, you're passing it 2 things, you're either going to have the value or the address, depending if you're passing by value or by reference. So those are passed those are pushed onto the stack. The return address, the second you make the call, the return address of where the next instruction is on the stack, and ESP is pointing to that spot. This slide, it's showing how we would pass an array by reference. So the only way that we pass arrays is by reference. Arrays are always passed by reference because the name of the array, remember, the name of an array holds the address of where the array begins. So as a review, when you have an array, boom, boom, this first element, let's say that this first element, it says FF00 is the first element. And let's say this is an integer array, so the next element would be a 04, 08, etc. If the name of this array is array, let's say, then the name of the array always, in all languages, right? If it's a C-style array, holds the address of where the first element begins. So the name of the array is a pointer to the first item in the first element in your array. So in this example, what they're doing is they're pushing onto the stack the start of the array and how many elements are in the array, like if this array has 100 elements. And then they call this procedure array fill. And this procedure, what it does is it has a loop, and the loop is going to go, from 0 to, in assembly, it goes from 100, from 99 to 0. And let's see, what is it doing? It's just filling the array with random integers. So anytime you pass an array to a function, for example, let's say that this is in C++, so this would be array fill. And if I was passing it this array, and it's size word, so size word is 2 bytes. That would be a short int in C++. Short. Because an integer in C++ is 4 bytes. we shorten it, and then the name of the array, and then our bracket, say that it's an array. Say that this was a void function, it would look like this. So whenever you pass it, what gets passed, it's a push and it's the offset. So this receives the address of the array that gets passed to this function. So here they're inside the procedure array fill. So again, the very first thing that these two steps have to happen every single time. EBP has to be pushed onto the stack. We have to move ESP to EBP. We have to push all the registers to the stack because they're about to change the registers. So it looks like they're moving. So here's the stack. And what the stack has is they push the offset and count, right? So the stack has the offset of the array. So I'm going to put address of array, and the stack has the value 100 because that's count. And when we make the call, the stack also has the return address. So I'm going to put RET, return, and then the and sign for address, because we know the and sign gives us the address. So once we go into the procedure itself, we push EBP onto the stack. EBP. And now this is where ESP is pointing to. Remember, ESP started here, added ESPs here. That's the stack pointer. And remember that what ESP holds an address. It's holding the address of this spot right here, which is an array. So ESP holds an address. And I'm gonna put some addresses on this. So I'm gonna say put FC A. I'm trying to make it. I'm trying to make. If I make this 0, 0, and this would be 0, 4. Apparently I can't count backwards. This would be 0, 8. And then plus 4, 8, 9, 10, 11, 12, ABC. Yeah, okay. So FC, F8. So let's say this is the address. So what ESP has in the register, if I looked at it, it would be an address. Blah, 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 0, 0. That's what ESP holds. And then they move ESP to EBP. So EBP, also an address, right? EBP is saved here. Now they're going to overwrite it with what ESP is pointing to, which is some address 0, 0, this spot. So EBP points to the same spot as ESP. Then they push all the registers onto the stack. So that's a lot of pushes. Bomb, ESP moves. Then they move EBP. Now see, EBP is pointing here, right? We know where the base is. Even though we did this push and ESP has moved all the way down, EBP is still at the base pointer. So we know that the values that were passed to the function are always going to be, like if there's 2 that got passed, then you're going to go EBP plus 8, EBP plus 12, always. So to get to the first, or to the second parameter that got pushed, you do EBP plus 4 gets you here, EBP plus 8 gets you here. So EBP plus 8 is the counter, ECX. So that's that 100, that sets the loop counter. And then EBP plus 12 is this here, which is the address. That's why I put the and sign. It's the address of the array that gets moved to ESI. Now you can do a loop and fill the array with random numbers. Okay, so let me see what comes next. I might stop here and do a little exercise. Oh, they had a picture. Looks a lot better than my picture, but the same picture. Okay, yeah, so we're gonna stop right here. And what I want you guys to do with me, we're gonna code this example right here, okay? We do a little bit different. Instead of doing array fill, what we're gonna do is we're gonna go ahead and fill the array with some numbers, and we're going to just accumulate the values in the array and push them to this procedure. So this is an example that I showed earlier. Take all this out. So remember, whenever you add a procedure, make sure to always remember to add RET, because if you forget RET, you get an exception, because it doesn't, RET is what returns you to this spot. So the program, when it gets to here, it doesn't, like, it's lost, it doesn't know what to do. Let me just run this, make sure that I don't have any errors and everything runs okay. And so the first thing I'm going to do is I'm going to declare an array of word size. Let's make it double word, make my life easier. And I'm going to put the values 10, 20, 30, 40. So that's 100. And what I want to do is I want to accumulate these values, but I want to pass those values on the stack. I want to pass the array to the stack and the count. And so if I do this sum array doesn't matter. It doesn't matter what size array I have. It doesn't matter. Yeah, it doesn't matter what size array I have. I could have 10 elements or 20 elements or 1 element. It's going to work for everything. So in my main, so I'm going to do like they did. So I'm going to do count. But instead of putting 4, I'm just going to say the length of array. That way it's going to work for any size array. Okay, so before we call the procedure, we're going to push our parameters. So we're pushing, it doesn't matter which order, you just need to know where they're at. So I'm going to push count first to the stack, then I'm going to push the offset of array. Okay, so I have I did it backwards. They did the offset first and then count, but doesn't matter. I know where they're at. And then we're going to do a call. That call is going to put that return address. So we're going to do a call to sum. Okay, so now when we move to sum, the first thing that we want to do is push EBP. Then we want to have EBP point to the same spot that ESP is pointing to. So move ESP to EBP. So now I need to get to these two parameters. So the way that I get to those two parameters is by saying EBP plus 8 and EBP plus 12. So the way that I did it, I pushed count first. So I'm going to move to ECX, EBP plus 12, because that's where my count is, and that's what's going to what I'm going to use for my loop. That's what's going to control my loop. And then I'm going to move to ESI. EBP plus 8. So now ESI holds the address of the number 10. So ESI is pointing to my array to the value of 10, and ECX has 1, 2, 3, 4 is the number 4. So then I can do a loop, L1. L1 is controlled by ECX. And then every time I can, maybe I can use EAX to accumulate. So I would add into EAX, ESI. So the first time, ESI is pointing to the 10, so it moves 10 to EAX. And then I've got to increment ESI so that it moves to the 20. And I'm going to increase it by the type. So the type, we know that the array is a double word. So I'll have to increase it by 4. So probably what would have been better is if I would have actually passed the type to it. And then it would work for any type. But right now it's just going to work for one type. So here we're going to add the ESI 4. So again, the first time ESI contains a 10, it adds it to EAX, and we add 4 to ESI. That takes you to this next address. If I don't put the brackets, it gets me the address. If I put the brackets, it gives me the contents. So it dereferences the address. So by the end of this loop, EAX will have the sum. And so I can put a breakpoint and test that. Before I test it, there's 2 things that have to happen before I leave. There's actually more than, so I need to restore my EBP, and so I would do pop EBP. And then once you pop EBP, then you're at the return address. So then automatically RET is going to pop that return address and take you to this spot. Okay, so let's see if this works. So what are we looking at? So right now, EAX, let's see. Oh, one thing that I didn't do, so EAX has this big number here, and at this point, it should just have a 10 because it's adding the first value. So what I didn't do is I didn't zero out EAX. Since EAX is an accumulator, we have to zero it out because it always starts with junk. So we're going to move 0 to EAX. There we go. So now we move 0 to EX, cleared it out. We added 10 to EAX, so it has a 10 there. Don't worry about all this over here. We added 4 to ESI, so ESI is going to point to the next number. So, oh, goodness. Don't want to put that in the loop. That's going to clear out my, it's going to clear out my EAX every time. Okay, let's do a breakpoint here because I want to see ESI before we add 4 to it. Okay, so we clear our EAX with this line. Then ESI contains this value right here. So the next time we're going to add 4 to that, so it'll be 45. Okay, so right now, at this point, it's going to get the value of 10. It's going to add it to EAX. We're going to move 4 to ESI. So, where's ESI? I was looking at the wrong thing. ESI is this one. I was looking at EAP. So ESI has 4,004. So now we added 20 to 10, and it's in hex. So what you're seeing is hex. But we can watch EAX here in the watch window. And we can change our view to decimal, unsigned integer. So there's 30. So 10 plus 20 is 30. We add ESI to EAX. So now we have 60. Then ESI gets another 4. 64. And hex, 100 in EAX. So at the end, EAX contains the sum of these values. And so it pops CVP, and then now it's going to pop the return address and see how it takes us to this spot. That's the return address. That's how it knows to go there. Okay. So here, the nice thing about this code is that we can change this array and add more values. And it doesn't matter how many values you add, it's going to work. And at the end, it's going to have the sum. So 170, I added 70. And they'll work every time. So it's going to work for any double word array, any size. And if we wanted to make the type, like if we wanted to change the type, we could do that too by passing the type to the procedure as a third parameter. Okay, so this next slide, it talks about accessing stack parameters. We just did that. So accessing stack parameters is doing this right here, EVP plus 12, EVP plus 8. I talked about return. So return always pops the stack, and it pops the address onto the instruction pointer. Now there's another way that we can call return, and then N is going to be number of bytes. And what that does is before it returns, it cleans up the stack. So right now, we're not cleaning up the stack. So on the stack, what's left is offset of the array and count when you return. So there's two ways that you can clean up the stack. We can manually clean up the stack. So when we return, we could do two pops. So pop into some register like EBX, pop, EBX. So that would clean up the stack because that would get rid of, that would pop those two values off. You could also clean up the stack by after popping EBP. Well, you've got to return. So you could also move ESI. So once it returns, you could move do ESI minus 8, 8, 4, 8. Yeah, minus 8. 8. So it returned ESP is going to be here, so it'll be 4 a.m. So you could do this and not the stack pointer, ESP. So after it calls and it pops off the return address here, then you could move ESP1. It would be here, you would move it up. So you could do that manually, but instead of doing that, you can also do return 8, and it would clean up those two values on this that are left on the stack. So that would subtract 8 from ESI. So that would do the same thing as this right here. So N is an optional operand. It causes N bytes to be added to the stack pointer after EIP is assigned. Oh yeah, I always want to subtract. We're subtracting for the stack to grow. We're adding, so we actually have to add. So this would be a plus. Oops. This would be a plus here. So this line would be the same thing as return 8. Just adds 8 to ESI. It adds N bytes are added to the stack pointer, ESP. And I keep saying ESI, that's not ESI, that's ESP. Oh. So ESP plus 8, not ESI. Okay, so here they just did add ESP comma A. Well, that's a lot easier. So same thing. So you could do add 8 to ESP, or you could do return 8. So that cleans up the stack. So here's a procedure that you can practice with. You're going to create a procedure named difference that subtracts the first argument from the second argument. So you would push 14 onto the stack, you push 30 onto the stack, and then when you call difference, EAX would contain 16. So see if you can do that without looking at the answer on your own and practice. You're going to be turning in the example that I just coded, and you're going to turn in this example also as one of your exercises for this chapter. So again, try to do that without looking at the answer first. And then here you have an example on passing 8-bit and 16-bit arguments. So when we pass arguments on to the stack, we cannot push 8-bit values onto the stack. And we talked about this in chapter 5. We could only push 16 or 32-bit values onto the stack, or 64 if we're programming in 64 bits. So pushing 16-bit operands may cause page fault or ESP alignment problems. It's also incompatible with Windows API functions. Expand smaller arguments into 32-bit values using MoveCX or MoveSX. So going back to this instruction, if you have something that is 1 byte, like char val right here, just move it to EAX using CX. And then once you move it to EAX, then you can push it onto the stack. Here is an example of moving multi-word arguments. So you want to push high order values on the stack first or backward in memory, resulting in little Indian ordering of data. For example, if you have a double quad word, that's 1, 2, 3, this whole hex value. It's saying that it's best to push the long vowel plus 4, so the high double word first, then push to the low double word. So again, onto the stack, the max that we can have is a double word. So if you have quad words, which you would have in 64-bit programming, you would have to push your quad word in half. So you'd have to push the high double word and then the low double word. You have to break it up in half. Saving and restoring registers. Push registers onto the stack just after assigning ESP to EBP. So this is if you are using registers, after you move ESP to EBP, then push those registers onto the stack. So basically, you would have the registers that you push would be under EBP. So your registers would be here and here. Any registers that you push would be under EBP. Okay, so that was saving and restoring registers. Okay, so stack affected by the uses operator. So we've used the uses operator, and remember the uses operator automatically will push these registers to the stack. So when you call uses, ECX gets pushed to the stack and EDX gets pushed to the stack. So this code right here, you don't have to have this. Automatically uses will do this code and it will do this code for you. So you can create a procedure to put uses next to it. So let's do that on this example that I just did so I can show you what that looks like. So right here in my example for the sum procedure, I'm using ECX, I'm using ESI, and I'm using EAX. So I can save those values on the stack. Like I could just push all 3 of them here after I could push them here. Manually, I could have 3 pushes. but I don't want to do that. I'm going to do it here. I'm going to say uses ECX, ESI, no commas, and EAX. So automatically by me putting uses, it will save those, push them onto the stack, and then restore them at the end.
Yeah.
Okay. Local variables. So local variables would be variables that are defined inside your procedure. So let's say that I have int x inside my function, then that would be a local variable. So only statements within subroutine can view or modify local variables. Storage used by local variables is released when subroutine ends. So you know when a function ends, you no longer have that value available to you. Local variable name can have the same name as a local variable in another function without creating a name clash. So we can have two functions with the same local variables. Each one will have its own separate address, and each one will be in its own stack frame. Essential when writing recursive procedures, as well as procedures executed by multiple execution threads. Okay, so let's take a look at local variables, the way that they work. So here you have EBP, right? This is the base pointer. And if you had passed any values to the function, they would be here above the return address. So you'd have your parameters are here. Parameters. Return address, save EBP, EBP points to the spot. Any local variables to your function are going to be under EBP. So if you have local variables, you push them onto the stack by subtracting from EBP. To get the parameters, you add to EBP to go up and get those. So you make room below EBP to put your local variables. So here they pushed EBP, they moved ESP to EBP, they subtracted 8 from ESP. That means that they've made room for these two double word variables. Subtract 2, then they moved the 10 onto the stack, then they moved the 20 onto the stack. So in C++ is the same way. Anytime you have local variables, you're going to find them on the stack under the EBP where EBP saved. Okay, so we're throwing in this LEA instruction. LEA instruction returns the offset of some memory location. So you can either use the word offset or you can use LEA. So LEA returns the offset of direct and indirect operands. Offset operator only returns constant offsets. LEA required when obtaining offsets of stack parameters and local variables. So you have to use LEA if you want to get the offset of a stack parameter and a local variable. So here's an example. We have this procedure, copy string procedure. Now, this is a little bit different. So here, they're passing the values like you would pass the values in a high-level language. So you see this comma here after proc. This is the first thing that's getting passed to the function. This is next item that's getting passed to the function or to the procedure. So there's a count of size double word, and there's a local array of bytes. So, so these two items are getting passed to this function. So here, if you want the address of count, we can't use offset. They have to use LEA. So this gets the offset of count and moves it to EDI. This gets the offset of temp and moves it to ESI. So temp is an array of 20 bytes. And this is how you list them. You put the name of the variable, colon, and then the size. So this is a parameter. And actually, this is not a parameter. This is just a local variable. Sorry about that. I didn't see there would be a comma right here. There's no comma. So this is a local variable. This is a parameter to the procedure. So let's say that this was in C++. You would have copy string count. So double word is like an int. And then you would have count. So that's a parameter. That one. The local variable would be inside. So it would be like char temp 20. So that's that. And that one's that one right there. Now, so we hadn't talked about passing values like this with the comma, and then the way that we were passing them was by doing the pushes. If you pass the value like this, where you put a comma and then you put it next to it, it does the push automatically for you. So it pushes count to the stack and it will pop count off the stack. Here it pushes the local variable to the stack and it also pops it off. So that's the advantage of using this method. Okay, so we're gonna stop there, and in the next video, what I want to do is I want to actually go through and create some procedures that use this method, because you're going to be using this in your final, where you created a procedure and you have values that you pass to it. Okay, so we'll look at that and see how that makes it easier, so we don't have to do all those pushes and push and pops. And